Hello everyone, it's me Nazım Kerem Mert. At the beginning, I apologize for the my voice and maybe coughs during presentation due to I tested positive for COVID-19. So let's continue with our project for 543 lecture, which is cat-dog distinction. I prepared this project with Fatih Çemen. And our project have three methods, which are fully connected neural networks, convolutional neural networks, and generative adversarial networks. We all did these parts together with Fatih, all together, and we used the first two fully connected and convolutional neural networks for cat-dog distinction. But actually, the generative adversarial network is generating an image from nothing actually. So this is different from the other two. So we define our problem as cat-dog distinction because they are the most popular pets. And to do this, our problem is taking an image as input and try to differentiate cats and dogs. So we use the dataset which is retrieved from kaggle.com, and this dataset contains 4K images as a training dataset and 1K images as test dataset. But as you can see here, we have also a validation dataset, and we take this dataset with splitting the test dataset into two. So let's start with fully connected neural network. Fully connected neural networks are feed-forward type of network, and it takes only the flat inputs. Each neuron is connected to every neuron in the previous layer, and each connection in the network has its own weight. So let's move on to the code part. So we take these images from our IPython notebook file. So we start with preparing datasets. First we download the dataset from kaggle.com, and then we set the pets for training, validation, and test parts. So after setting their pet, we need to prepare each image in a dataset. So we actually do these transformations for training, validation, and testing datasets. But this is an example of training. In addition to other two, there's a random horizontal flip, as you can see here, with a probability of 0.1 to have a better training. And we have a resize function, which resizes to 28 times 28. Pixels in image, and it also transforms pixels to tensor. So now you can see the visualization of the data from training set, the first image, as you can see at the right hand side, 3 for the RGB red, green, blue, and 28 times 28 are the pixels. And this is the helper for visualization, which is a torch image show function as we defined here. So here we create the data loaders for training, validation, and test. So we need this for the checking accuracy of the network and the training part. So now we are creating our connected network with three fully connected layer. The first one is 2352, which is 3 times 28 times 28, which is our input to 1K. The second is 1K to 32, and the third layer is 32 to 2. And now that 2 is, one is cat and the other is dog actually. And this is the initialization of the network, and this is the forward step of the network. As you can see here, we have linear functions also as a ReLU. And at the end of this part, you can see a mock input, test input from our input to see the output of the network. In here, we select our loss function and optimizer, which is cross entropy loss, which is common to use with softmax function at the network, and our optimizer is Adam optimizer. So in here we define a function which calculates the accuracy, and actually we use this function before training, during training, and after training. So that's our function actually, which takes images and labels from the data loaders. Here you can see the test accuracy before training, which is 49.96, which is very close to 50% as expected, because half of the images are cat and half the other half is dogs. In this part, you can see a one epoch of training, which take images and now reshape it to the flat inputs for our fully connected network and our optimizer and loss functions. Now you can see our training loop at the left-hand side, and we have a 30 as a number of epochs. And also we print the training accuracy and validation accuracy after each epoch. And you can see the results at the right-hand side. You can see the training accuracy and validation accuracy are increasing with the number of epochs as expected. So in this part, you can see the results of training in a plot. So we plot the training accuracy list as blue and validation accuracy list as orange. So now you can see that the test after training, which is 65%, and this is maybe a little bit low because we have input sizes with 28 times 28, which is also small size of input, and this is a fully connected network, so this is not a convolutional network, or it's actually not a deep network too, so this is also expected for these reasons. So thank you for listening to me. Now my friends and my project partner Fatih will continue to present.
Hello, my name is Fatih. Today I will talk about the second part of this project. The remaining methods are CNN and GAN. Convolutional neural networks, or otherwise known as CNNs, are deep learning models that are most commonly used for computer vision applications such as classifying images. A regular neural network has an input layer, hidden layer, and output layer. So what makes a CNN unique from other neural networks? CNN work differently as a result of the model treating data as special, rather than neurons being connected to neurons in the previous layers, as in fully connected neural network that Kerem has mentioned. In convolution operation, the neurons within a CNN are only connected to neurons closely, and they all have the same weights operations during convolution. So it uses local specialty. Let's look at CNN structure. In fact, the convolution layers are the major building blocks used within SCNNs, and they are the most important components of this network. And additionally, we have pooling layers. And what is pooling layer? A pooling layer reduces the sample size of a feature map and additionally makes processing faster because it reduces the total number of parameters a network needs to process. The output of a pooling layer is a pooled feature map. There are two ways to create a pooled feature. These are max pooling and average pooling. As an example, let us elaborate on max pooling. Max pooling throws away these least important features by picking the maximum value of the pooled feature map. For example, for those four features, we select 6, 8, 3, and 4 among these features, so it reduces the sample size of the feature map. Let's continue with our CN implementation. I use same dataset with Kerem, Kaggle datasets, and as he already mentioned, we split the test dataset into two parts, which are validation set and test dataset. We have utilized some transformations while preparing datasets in order to increase random nature of the neural networks. We use some horizontal flip with some probability in order to increase the randomness. Also, we use 100 to 100 resizing and tensor operations. These are the visualization of data. As I have already mentioned, this is 100 by 100 pixels. Let's continue with convolutional network structure. We start with three input channels. These are RGB and output channel 16 with kernels at 5. This means 5 filters moving around our filters, and stride is equal to 1, which means the number of pixel shifts over the input images. And for full connected layer, the feature map downscales to 2, which is used for get-top distinction. For activation function, softmax is selected because with cross-centric loss function, this is commonly used in classification. Again, this is loss function, this cross-centric softmax is selected because softmax and cross-center flows are commonly used for classifications, and our project is about classifying dog and cat images. As an optimizer, we use ADAM because it's very standard and it works very well. We calculate the accuracy both before training and after training. Before training, the test accuracy is 50%. This is expected because there is no training, so this is random for knowing which one is the correct image. We use 30 epochs for training group, and we have improved training accuracy from 63% to 93%. Result of training, it increases to 90%, as it's seen. Finally, we evaluate our models with test dataset, and the test accuracy after training is 81%. This is good, but not enough, and training accuracy can be further increased by increasing convolution layers from 3 to 50 layers. The final method is GAN. GAN is an unsupervised learning task in machine learning that is used for automatically discovering patterns in input data. And basically it has two models, generator and discriminator model. Generator model is used for training to generate new examples, and discriminator model tries to classify examples as either real or fake data. And these are the successful image generations for MNIST datasets. All of these are successfully generated. I want to thank you for listening to us.